And we're back. And now it's time to talk about vector performance. Now remember, we heard that the high level of sophistication provided by vectors can sometimes come at a performance cost. Now we haven't run into it yet, but it's there, it's a threat, and it's something that you need to understand and prevent if at all possible. Every time you create a vector, it starts off with a specific size. It can grow dynamically as you need it to, but every time the vector pushes past its current size, the computer has to reallocate memory. Now, sometimes the computer might even have to move the vector to a completely different location in memory, based on where the computer has room for it and where it doesn't. It's this process of copying the resized vector to a newly seized chunk of memory that causes a performance hit. Now you have to think about whether or not this possible performance hit really matters. If it's going to happen in a part of your program where timing is important, then you can't really ignore the problem. Performance hits cause slowdowns, and you don't want the program slowing down when timing is crucial. Now, if you've ever played Quake or Unreal Tournament or any of those first-person shooter games, and notice that the game's frame rate slows to a crawl when there are a lot of players or enemies in the room, that's one possible result of a performance hit. Now, on the other hand, if the memory reallocation might not happen during a performance critical part of your program, then you might not care about the performance hit. Or maybe the vector is so small that reallocating the memory for it won't amount to all that much. And in those cases, you might be able to safely ignore performance issues. Now, the way we control or help control memory allocation is through a couple of the vector object's member functions. The first one is capacity. The capacity member function returns the capacity of the vector, the number of elements that a vector can hold before a program has to reallocate memory for it. Now, this isn't the same as its size. Size is the number of elements the vector currently holds. Capacity is the number it can potentially hold. So let's take a look at how that works. We've got a new C++ document, and a new text document, and we're going to save it in week 6. And I'm going to call this capacity.cpp. And we're going to just say that that's a capacity demonstration. We need to include IOStream. And we need to include vector. We declare that we're using the std namespace and open our main function. And we'll say that we're creating a 10-element vector to hold scores. So we'll create a new vector with ints called scores, and we're going to go ahead and set it to 0 in all 10 elements. Now, we'll see out vector size is scores.size end line. Now, vector capacity is scores.capacity. And I left off my quotation mark here. Okay, scores.capacity end line. Okay, so the first line will display the current size of the vector. The second line will display the capacity, how many vectors or how many elements the vector could potentially hold. Now, we'll say that we're adding a score to our vector, and we will push back 0. So the memory will be reallocated. Now we'll say our vector size is scores.size, followed by an end line, and vector capacity is scores.capacity, end line. Okay, we'll return 0 and close our main function. I save my document and I will compile it. And run it. Okay. First 3 lines. We created a 10-element vector to hold scores. We said that the vector size is 10. Vector capacity is 10. I should have added a space there. I'll just have that there for later. Then we added a score. Now our vector size is 11. But if you look, you see the vector capacity is 20. Okay, every time a program reallocates memory for a vector, the vector's capacity doubles. If we kept adding elements past 20 to, say, we had 21 elements, we would expect to see the capacity changing to 40 instead of 20 because it doubles. Now, there is a way around this. We can reserve a specific capacity for our vector from the get-go using the reserve member function. So let's look at how that works. I'm just going to save this as a different document. I'm going to stick with my same code just to save on typing. And we'll call this one reserve.cpp. Okay. Vector size, vector capacity, we leave as is. In fact, these first few lines we don't need to change because we still need IO stream, we still need vector, and we're still using the same namespace. We create a 10-element vector to hold our scores. We declare our integer vector with 10 in all 10 slots. And then we output the vector size and the vector capacity. Now, we are going to reserve more memory. Instead of pushback 0, we're going to have scores.reserve 20, and that will reserve memory for 10 additional items. Then we'll output our vector size, our vector capacity, and we'll see what happens. So I'll save that. G++ reserve.cpp and run it. Okay, so now we start off, we create a 10-element vector. Vector size is 10, vector capacity is 10. Now we say that we're reserving more memory. Vector size is still 10, but now the capacity is 20, even though we haven't added any new elements to it. we've reserved additional memory for it. Now, by using reserve to keep a vector's capacity large enough for your needs, you can basically dictate when this memory allocation is going to happen. You can delay it until you're ready for it to happen. For example, when the game isn't quite so fierce or intense and the performance hit won't cause problems with gameplay or with the way the program runs. Now, the last thing to consider for performance is what happens when you add or remove an item from your vector. The pushback and popback functions are super efficient. They're great at adding to the end of a vector or taking away from the beginning or end of a vector. But the problem that we have is when we're adding or removing an element somewhere else in the sequence, like in the middle, like when we use insert or erase. This requires more work because the computer has to move multiple elements around in order to handle that insertion or deletion. Now, with a small vector like we've used, the overhead for this is pretty insignificant, not really noticeable. Now, with a larger vector, say one with thousands of elements, you would see a definite performance hit when you try to add or remove from the middle of that vector. And there isn't really any easy way to fix that type of a problem. So this might make you think about using a different type of container. If you've got a large group of data and you know that you'll need to add or remove from anywhere other than the beginning or the end, look at the other containers provided by the STL. One that might work for this is the list type. The list object allows for very efficient insertion and deletion no matter how large the sequence is. The moral of the story is this: vector is very versatile. It's probably the most popular container type from the STL, but it isn't always the best choice. You have to think about how much data you're going to be storing in the container, how you're going to be manipulating it, and then decide which container type is best suited to your needs. On table 4.1 in your textbook, which should be on page 139, there's a list of the different container types provided by the STL. Okay, so that's it for vector performance. Next time around, we will look at another way to plan out your program using what's called pseudocode. And then we'll put that to work in creating a version of Hangman. So stay tuned for that, and until that, have a great day, and let me know if you have any questions or problems.